See, for a symmetric aerofoil, if this is the V, this is the V, and this is the chord line, this is the chord line, and if I join this, this is the chord line. What do we notice here? Remember, chord line we defined as, if you join leading edge and trailing edge by straight line, that becomes the chord line. Similarly here, the leading edge and trailing edge have joined, and that becomes the chord line for a cambered aerofoil. This is cambered, and this is symmetric. Now, what is in your mind? If the air is coming like this, do you think this will produce any lift? The answer is no, because we remember, as far as George-Cayley's guideline to us on the concept of generation of lift, lift will be generated when there is an angle between the velocity and the surface. In this case, there is no angle, so it will not generate any lift. So if I draw CL, which is nothing but lift divided by half rho V square S versus angle at alpha equal to 0, I will also get 0 lift or 0 CL. But for cambered, you see, the very fact this chord line is no more parallel to the velocity vector, you could see actually effectively it has an angle with velocity vector, even if it is at alpha equal to 0. Similar condition. Okay. So in this case, what we will see that even at alpha equal to 0, there will be some lift. I repeat this. One way to explain is this chord line, and there is no angle between chord line and the velocity vector. So what we talk about alpha equal to 0, or same velocity condition, it will produce a 0 lift. But here, because of this camber, because the camber is there, there's some angle, some surface is there, which is making angle with the velocity vector. So even at alpha equal to 0, it will produce lift. As I increase this angle, what will happen? As I increase this angle, what will happen? There will be more lift, because from this George-Cayley's explanation, the lift will be function of angle for a given area, given other conditions. So as I increase the angle, the lift will increase. So you will find up to certain point, lift will go on increasing as alpha is increased. But beyond a certain point, you will see that beyond a certain alpha, you will see that lift is no more increasing. In fact, it is going down like this. Similarly for here, going down like this. What exactly is happening? Typically here, if I see, there is a limit which we call alpha stall, and this value we call CL max. Similarly here we call it alpha stall, and this is CL max. What we say that beyond a certain angle called alpha stall, the flow will no more remain attached. There will be a separation, and there will be a stall, and the lift will reduce and drag will increase, right? Flow will no more remain attached, or there is some sort of a flow separation. What is actually loosely happening, if you see, if an aerofoil is an angle, right? Now see what is happening here. The airflow is coming like this, Now as it comes backward, it's a relative here, right? What again we are seeing that if I take a control surface, I see here as the air particle moves in the backward direction, the area at 1, 2, 3, 4, all this station, the area is going on increasing for a given control surface. So area increasing means the velocity v1, v2, v3. So v1 is greater than v2, v2 is greater than v3. That is, as area is increasing s, so maintain the same amount of fluid flow, the velocity has to reduce. So v2 will be less than v1, v3 will be less than v2, v4 will be less than v3. And this implies the pressure at 3 is greater than pressure at 2, pressure at 2 greater than pressure at 1. So it will experience a adverse pressure gradient. Okay? Or at this stage we only talk about adverse pressure, and this adverse pressure will try to discourage the fluid particle to move in this direction, and moreover, because of skin friction, already some part of energy of the fluid is taken out. So there will be an angle at which the flow will not be able to move backward. At some point it will separate, right? And that is, we say the flow is no more attached. Stall is much more than this, but we need to know that when you are talking about this zone where it is almost linear, I am talking about attached flow. And when I am talking here, I am talking about separated flow. There is a sophisticated aerodynamics to explain all these things. We are not going deep into it. We only need to understand one thing, that for symmetric aerofoil, I can write model CL as dCl by d alpha into alpha. What is dCl by d alpha? dCl by, because it's a linear straight line, almost straight line, right? So here this is the slope. When I say almost straight line, in practice we'll find beyond 6-7 degrees some sort of a nonlinearity comes, right? So but we are assuming here up to this point this is straight, so I can write CL as slope of this into alpha. But for cambered aerofoil, I will write CL as CL naught plus CL alpha into alpha. This is just a question of, because for cambered aerofoil, I will be actually doing it like this. At alpha equal to 0, there is some CL, which is I will be referring to as CL naught. So I can model CL as this. In textbook, when we try to distinguish between CL because of aerofoil and CL because of wing, we use strict nomenclature. For aerofoil, we use C small l, and for wing, we use C capital L. Of course, in aerospace there is a confusion. Even for rolling moment we write CL. So let's be very clear, we are talking about lift coefficient. So for aerofoil I will write CL equal to CL naught plus CL alpha into alpha, where CL naught equal to 0 for symmetric and CL naught not equal to 0 for cambered. And for wing I will write CL equal to CL naught plus CL alpha into alpha. Again CL naught is 0 for symmetric and CL naught not equal to 0 for cambered. Right? Why this is important? You will soon realize that as far as flying a machine is concerned, if I had to maintain lift equal to weight, right, I need to fly at a particular CL, which will be governed by the weight, speed, etc., etc. But the question is, how do I generate this CL when I'm flying? The pilot, how will he generate? That answer will come from here. If I know what is CL naught of the airplane, if I know what is CL alpha of the airplane, then I know if I have to generate a CL which I know a priori, then I know how much angle of attack I should fly, so I know how much I should turn the airplane, right? So this is that is why in performance this is important. At the back of your mind, please. Now I am talking about aerofoil and wing. For the whole aircraft, we'll try to find out. For whole aircraft, we'll try to find out. For CL aircraft, what is CL naught of the aircraft, and what is CL alpha of the aircraft into alpha. Please see the distinction. First one is aerofoil, second one is wing, and third one I am talking about aircraft. But now what is the difference between aerofoil, wing and aircraft? Why we are using these three terms? Let us see that. When I am talking about aerofoil, imagine aerofoil is basically a 2D concept, right? 2D. That is, imagine this is, you have seen this an aerofoil shape, and imagine this having a span infinite, that is infinite here, infinite there. So what is the basic message is, as the flow is coming like this, it has no way to go towards cross right or left. So always the flow is over the each aerofoil section. So there are no flow around right or left because these are infinite span. So that is why we call aerofoil is a 2D concept, right? But in actual practice, what happens? See, when I come to the wing from here, when I come to the wing, many textbooks use a word called finite wing. This finite comes from here, the aerofoil, they are infinite span. So no cross flow is allowed, only all the flow are along the chord of the aerofoil, right? Now when there is a finite wing, that means this is not infinite. Let us see what happens. If it is flying at an angle like this, the pressure here is more than the pressure on the top. That is why there is a lift. As I come near the tip of the wing here, what happens? Here the pressure is more and pressure is less. So air will try to come from the bottom to the top, and they go on forming a vortices like this, right? And since they go as a rotational, go into a rotational motion, vortices are formed, so rotational kinetic energy is required, and that comes at the cost of the energy of the airplane, so we call this actually induces drag, right? So that is why in finite wing we have wing, tip, vortices. If I draw the diagram, if you see, this is the wing cross section I am drawing. This is the span. Right? Let's say this is the fuselage. Now what is happening? Because if there is a lift, that means pressure at the bottom, they are more as compared to pressure at the top. So what is happening at the tip? Because this is high pressure, so flow will go like this, and they form vortices which draws rotational kinetic energy from the energy of the airplane, and hence energy is lost and it affects the speed. So we call it drag because of these vortices, or we call these as induced drag. Induced drag because of these vortices. So many times they are called vortex drag, many times they are called lift induced drag. Why lift induced? Because these vortices are formed because of the lift. Because of the lift there is a pressure difference, and because of finite wing there is a vortices form at the tip, and so it is a vortices drag, induced drag, lift induced drag. Note here, if I make it infinite, then this situation will not come. So it becomes a 2D, or it becomes an aerofoil. That's why aerofoil will never encounter conceptually any such vortex or lift induced drag, right? So that is, one is finite wing. Then we use for the aircraft, CL for the aircraft. So we started with aerofoil, where in finite span, wing, finite wing, we found there is a vortices, and because of the vortices there is a drag, and because of the vortices you will find the vortices will be coming like this, so they will be inducing a downward component of velocity, so the local angle of attack at the wing or even at the tail will be changed, will be reduced, so effectiveness will go down. So in a language of airplane aerodynamic modeling, we can always say that the lifting characteristic gets changed because of downwash, or the CL alpha may also change because of downwash, right? Now for CL alpha of the aircraft, or CL of the aircraft, we write CL because of wing, CL because of fuselage, CL because of tail, plus CL because of miscellaneous component. That is to say, if I know what is the CL alpha of the wing, if I know what is the CL alpha of the fuselage, and if I know what is the CL alpha of the tail, and assume that all of them are based on same reference area, then here if I simply add these things together, then and expect that that will be CL alpha of the whole aircraft, you may not be correct. In fact, we are not correct if we are doing like that. For simple reason, there are many such reasons, but one of those, see, this is the CL, when I am computing CL alpha of the wing, this is a wing in isolation. But in actual practice, what happens? When there is a fuselage, it gets, let's say, if this is the fuselage, then I am attaching it like this on the wing. So there is a body to wing interference here, right? Similarly, if I calculate for body alone, when I bring near the wing, there is a wing body wing interference. Same thing happens with the tail. So when I am talking about total CL of the aircraft, I need to take care of body, wing, body. Similarly for tail, interference factor, which modifies the overall CL of the aircraft. So that is why we use three terms distinctly. One was CL alpha of the aerofoil, understanding very clear, this is a 2D flow, that is, there is no cross flow like this, right? Second thing, where you use small l, CL capital alpha for a finite wing, where because of finite wing there will be vortices that will affect the drag and the lift curve slope depending upon the size. And third one is a CL alpha of the whole aircraft, which will be sum of CL alpha of the wing plus CL alpha of the fuselage plus CL alpha of the tail plus any other components are there. But we should be very careful that we have appropriately taken the interference factor between body, wing body, tail body, body tail, all in together, right? If I come back to CL again, I said this lift by half rho v square free stream into S reference, right? Similarly, you said CD as drag by half rho v square S reference. Again, this is free stream. We have been using the word free stream, right, and talking about S reference. Let us understand what are these things. Let us draw an aircraft. And let's say this is the relative air speed. Textbook, always you will see V infinity is written to explicitly mention that is the free stream condition. What is the meaning of free stream condition? We are trying to address that. If I come close to this body, so here, 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 what will happen, you see? Or here, for that matter. If this is V1, and if I take this point 2, will the velocity at point 1 and point 2 be same, or speed at point 1 and point 2 be same? We could see very clearly at point 2, because of the contour of this fuselage, there will be a change in speed here, because you could see at this point, again the area goes on decreasing if I take control surface. There is a natural tendency for the flow to accelerate. I am talking about low speed flows, right? Okay. So local velocity and the velocity of air further away from the body are different. Similarly, if I come here, by the time flow reaches here, there is a viscous effect on it, over and above the contour effect, and then the velocity will never remain same. So when I am trying to non-dimensionalize this lift or drag, which velocity should I take? Because at each point the velocities are different. That is why we take the free stream velocity, and the understanding is this: it is at a very far away from the body, so that there is no influence on the speed of the free stream. So it remains constant. That is why we talk about free stream, so that we can define a non-dimensional quantity consistently. Now, S reference for aircraft, S reference is the wing area. Wing is the primary component which produces the primary thing, the lift, and wing area is the S reference for an aircraft. And for a missile, you will find, if a missile is wingless missile, just it has got like this, you may find this maximum cross-sectional area, max, that sometimes becomes reference area. But coming back to aircraft, let's not forget, when I talk about S reference, it is the wing area. Okay. So what we have very quickly learned that when I try to model lift, I will model it like this: half rho v square. S means S wing, V means free stream, half rho v square is free stream dynamic pressure into CL. Okay? And CL is basically lift by half rho v square, which is the free stream into S, which is wing area. This is another observation on free stream dynamic pressure. If I draw an airplane again, if you see a tail here, and this is a V, the free stream pressure here, 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 and here could be different, because the flow, the energy might have lost. However, if I have an engine here, mounted here, this prop wash can create or augment, change the free stream dynamic pressure on the tail. So that is why we need to be very careful when I am talking about lift and drag, that when I try to finally talk about overall CL of the airplane, then it has to be non-dimensionalized with the free stream dynamic pressure. Okay? But local lift could be on the local dynamic pressure.